When rocks are deformed, you can get different types of responses given the conditions. Example, a piece of trash plastic. All right, if I were to slowly pull on this plastic, it's starting to slowly, plastically, ductily stretch. But if I was to pull really quickly, it'll rip. All right, so if I apply a stress very quickly, I can get a material to break. If I apply that stress very slowly, I can get it to behave more like a plastic. Now that's not just it. The type of material matters too. That's plastic, okay? What if I had a piece of, I don't know, wood? It wouldn't behave very plastic-like at all. So folds generally occur in sedimentary rocks. And why that is because when rocks are thinly interbedded and you apply a compressive stress, you can get them to behave somewhere in the middle between brittle and ductile. So it's not necessarily like Play-Doh, but what's happening is along each one of those little bedding planes, you're able to get the little beds to slip past each other. That's called flexural slip, and that accommodates the rock slowly compressing and creating folds. When you think about folds in their morphology, we can think about waves. Now, while they don't behave like waves in, say, physics, there are crests and troughs, just like you think of with waves, right? And so the crests are convex up or concave down. Those are the same thing, right? Those are called, generically, we would call that an antiform, right? Because it is shaped with the two limbs facing different directions. If we know that the rocks in the middle are the oldest, then we can classify that as an anticline. Right? Alternatively, we have that fold here. We have the convex down, concave up. That would be called a synform. If we know the age relationships, where the youngest rocks are in the middle and the oldest rocks are on the outside, that would classify as a syncline. Right? There are other types of folds as well. We can have a monocline. Monoclines are not really uncommon, and they're almost like a step up. So instead of having a true fold, you have just one, what we call limb, where you have a ramp up in the rocks. All right, there's several famous ones, specifically in and around the Colorado Plateau, the East Kaibab monoclines. One of them, this is a beautiful example right here. But those are our 4 or 5, I guess, major types of folds. Antiforms, and if we know the ages, anticlines. Right, we have to know the ages. If we don't know the ages and it's just shaped like this, it would be called an antiform. Right, synforms this way. If we know the ages and everything is upright, that would be a syncline. And then we have our monocline, and those are our major types of folds. But if you have rocks get folded like this and then they get turned upside down, well, that would still be an anticline that has been inverted. All right, that picks up several different names as it gets rolled over, but that is still an anticline that has been overturned. When we break down the parts of a fold or the anatomy of a fold, we need to give terminology to the different parts. These are really important when we're talking about the economic utility of folds, which can be everything from how groundwater moves, oil and gas. A lot of economic geology is dependent on folds, and so this terminology is really important when we're conversing with other geologists. So right in the middle of the fold, right, here's our anticline. Right up the middle, imagine a plane cutting the fold in half. Right? That would be called the axial plane. This is the axis. The axial plane would cut that in half. All right? If we imagine a single point running through there or a line running through there, that would be what we would call the hinge line. You can almost think of if there were a swivel and the fold were folding around it, that would be where we want to put that hinge line. All right, so axial plane, the hinge line runs down the axial plane. On both sides, we have what are called the limbs of the fold. So in this, you have a left limb, or right limb, or east and west, or whatever terminology we would use in the field. But the limb goes up to where you get this flat area. That would be your hinge zone. And then an axial plane cuts the hinge zone in half, separating the two limbs on each side.
A lot of times you'll get multiple structures, anticline, syncline, anticline, syncline, anticline, syncline, that overall form a much larger cohesive structure. So when that happens in the overall structure is an overall anticline, we'd call that an anticlinorium. And the opposite would be a synclinorium, where you overall have the exact same qualifications as a anticline or syncline, but there's many little folds in the middle. These are really common and again, really important when it comes to economic development of geology because this gives you your subsurface geometry that's much more complicated. Talked about that axial plane and that hinge line. And those are two things we can measure structurally to get an orientation. And so if we have an axial surface, we can take a strike and dip on that because that is a plane, just like anything else. We can also take an orientation measurement for if we have a fold and it's maybe turned a little bit, we have that axial line, we can take what's called a plunge and trend. Plunge would be the angle that the hinge line is below horizontal, and trend is the direction in which it dips down. Folds can have a number of different geometries, and describing them effectively means we need to understand the terminology. So the most obvious is a chevron fold, really sharp angled folds that form chevrons. If you know what a chevron pattern looks like, that's one. You can also get what are called cuspate folds, which are kind of wispy. You can get teardrop shaped folds that are going to be shaped like a teardrop. I really like this picture of what's called a box fold. Sometimes the rocks just kind of kink up into this box and you get really cool structures.
Once that folding is less than 120, so once that folding is less than 120, that's called an open fold. Once it gets down less than 70, that's a close fold. Tighter than, say, 30 is a tight fold. And then once we get down even less than that, closer to where the limbs are parallel, that is called an isoclinal fold. As in iso, same, clinal, dip, right? So whatever the way the isoclinal fold is facing, the two limbs are going to dip the exact same angle. The folds aren't necessarily perfectly symmetrical. So I keep doing my arms like this, but it's really possible these folds could get turned asymmetrically pretty easily. And so if you think about that axial plane, when the axial plane starts dipping one direction, that becomes asymmetric, and that direction that it starts turning over is called the vergence direction. All right, so in this case, the fold that I've made is verging towards your left, or I guess that theoretically would be west. All right, we have a couple other types of folds here. So these tigmatic folds are really common in medium to high-grade metamorphic rocks, where you get these kind of really squirrely little folds, everything kind of kinked up. Those are just the small bands within metamorphic rocks that are a different strength than the rocks surrounding it. They'll deform up and make these really tight little folds called tigmatic. You don't even pronounce the P. All right, these other types called drag, I call them parasitic folds. That's a more common term, at least in my world. Parasitic folds are really cool. So if you find these parasitic folds and they're starting to be shaped something like an S, that indicates that your shearing is towards your left, tops to the left, which would also be left lateral, right? And so if you see those, you need to keep going in the direction of the little S to find the center of the fold. Once you get up there, that little center, you're going to start to see these M shapes, symmetrical M's. That means you're kind of in that hinge zone. If you keep going over this way, you're going to get Z folds. All right, Z folds, same thing. They're going to be kind of a right lateral indicating of shearing, which means tops towards the right. These asymmetric folds will make Z's. That means that you need to go towards the right to get to your hinge zone. I like the term parasitic because they kind of represent the larger structure than these little parasitic folds kind of hanging on for dear life, but they tell you about the larger structure. Now, kink bands are also pretty common in metamorphic rocks, where you see rocks kinking up and creating these really defined little zones in here. In this case, this is a thin section with some micas that are really, really tightly folded up in there. But this can happen at outcrop scale, and sometimes this can happen at a huge scale. And we start to call that crenulation cleavage, or crenulation folding, or something, whatever you choose your terms, where you'll find all these little micas and all these foliations, that everything's kind of kinked up together. But these kink bands, a little more common than kink folding, kink bands are pretty common in metamorphic rocks. Now, and a lot of times, remember, folds are overall compressive, and we associate them with compressive areas. So that means we're very likely to find folds in relationships to faults. And so one fold that is very common to be associated with a fault is the anticline. You very commonly see that. So in this case here, we've got what's called a blind thrust fault in the ground, kicking up, creating a big anticline at the surface. A lot of times that fold will try to bust through and get to the surface, but before it can do that, it kind of pulls up and folds the rocks on top. That's called a fault propagation fold. And then almost all ramp scenarios, when we have a ramp and a thrust fault, the ramp pushes up. It's pushing those rocks up and over and creates a fault bend fold higher up in the overlying strata. Think about, so we have these faults up here. When do we get synclines involved with faults? Well, it's really common to find what's called a footwall syncline, where the rocks in the footwall have been turned up because of the overlying fault pushing up and over. Now, we think a lot about compression when we have faults, but in every scenario, both compression and tension or extension, you almost always have the other type of stress, right? If you push this way, you're going to push stuff out this way, very generically. If you pull apart this way, you're compressing this way. So you can find all different types of structures in just about any environment. But folds are really cool because think about your hand as rocks and you start folding them. Even within a fold, you're causing this extreme amount of compression on the underside of your hand, and then the over component, right there, you get those little folds. Those folds are your skin expanding or extending, so you get that tension and extension on top. That happens with rocks too, right? So you start pushing, compressing rocks, you start folding them on the surface, at the very top of the fold, in that hinge zone, you can have extension. So a lot of times you get paranormal faults, and a block will drop down. That's called a keystone fault. So they kind of look like this. Block drops down, you get that keystone faults, that keystone block at the top of an anticline. And then in the interior of the fold, just like your hand, you get compression. It's extreme compression. So you can get these different stress fields in a very small area. Now, when we start talking about topography, what do folds look like at the surface of the earth? And so this is my best example here. This is the Sheep Mountain Anticline in northern Wyoming. Absolutely gorgeous. And you can see this A shape. In fact, in this shape, it almost looks like a V because the fold is almost a map scale chevron fold. It's very, very prominent. That hinge zone is very small, and all these rocks are straight going into it. And it gives you this profile that looks almost like a V, but you can also get kind of this A shape. And you get that with either anticlines and synclines, but there is a small difference. In an anticline, which is what this is, the rocks are dipping away here, and you get this really sharp here. You can see how it's what we would call plunging towards the northwest. And so we've created this fold, and it's been tilted on its side. And so that's creating where the rocks are plunging into the ground. This middle area here, we'd call this the nose of the fold, where it noses over. So a syncline will do the same thing, but when you see this A or V or shape right here, it's actually plunging the other way. So think about the rocks are tilted this way, they're plunging the other way, so you get that A or V shape at the surface. So with an anticline, the A points in the direction of plunge. With a syncline, it's the opposite direction. Zoom right in here. These are really cool features. These are called flat irons. These little guys right here. Flat irons tell us that the rocks are dipping. So even from a surface standpoint, we don't have to go measure it. We see these. They look like like cast flat iron. That's where the name comes from. And when you see that, they're kind of pointed like this. That means the rocks are dipping this way, boop, boop, that way, like that. The pointed area is up dip. The area kind of expands out, it's down dip, and you can see those rocks are dipping towards your right. And if you look over on the far left side there, you can see these little smaller ones over there. That's a less resistant unit, but those are flat irons with the rocks dipping the opposite direction. Let's look at a few examples. All right, here's the Karoo Desert. This is South Africa. This is a bit of an offshoot desert of the Kalahari, more or less. And you can see this nice A shape. And so this is a good example of the rocks here are dipping towards the middle. The youngest rocks are in the middle. The oldest rocks are on the outside, so that's a big syncline. And you can see this big A shape, which means that the syncline is dipping to the east, or your right. All right, the plunge direction is to the right. This fold has been created this way, and then the western side is higher than the eastern side, and that gives us this morphology, an east plunging syncline. All right, here's another one. This is our monocline. So if we look over here, we see some rocks kind of gently sloping up before flattening out, and they kind of flatten out this way. If you've ever been to, say, the Grand Canyon, Moab, whatever southern Utah National Park tour, this is a place called Dead Horse Point. I think it's a state park. And you can go to one of the overlooks and see these rocks. They're kind of flat, and then they bump up a little bit, and they flatten out again. So this is a classic monocline. And because it's mono, one cline, it's just one limb. That's why we don't necessarily classify it as a different type of fold. All right, Central Appalachians. This is a cool one called Sidling Hill. This is a classic, actually. In fact, it's so classic, they used to have a rest stop where you could go check it out. I think they still have the rest stop, but you can't do the little walkover to check it out. But it's right off the interstate. I'm going to guess I-64 or 8, I-68. I don't know. Interstate, right there. And you can see this big fold, this big syncline. Then the mountain is held up by the most resistant unit that is the core of the syncline. Super cool, right? The rocks are folded up, the most resistant unit's in the middle, and so the whole ridge that runs for miles in both directions is held up by a resistant unit in the core of the syncline. Very cool. All right, the Elk Basin. This is actually called the Elk Basin Anticline. And if you remember the word basin from 100 level geology, you'd go, oh, basin is where the rocks all dip together in all directions. Sure, that is true, right? So rocks that all dip in the same direction, would be like a syncline on all sides, would be a basin. This, in fact, though, is a different use of the term basin and the fact that just sediment was going in there. And this structure you're seeing here is the Elk Basin Anticline. But you'll see it terminates on both sides. You get those A shapes on both sides. And those are there because the anticline is plunging. If you're in the north side, it's plunging towards the northwest. If you're in the southern side, it's plunging towards the south, southeast. And so it's a, quote, doubly plunging anticline. All right? You can have these with synclines too. A doubly plunging syncline just means the two synclines are pushing towards each other. If you have a very large area that's depressed, that would classify as a structural basin. That would be like the Michigan Basin. If you look at a geologic map of Michigan, it looks like a bullseye. All right? Very similarly, some places are domes. Dome is the opposite of a basin, of a structural basin. Forget the Elk Basin part, a structural basin. A dome, a structural dome, is where the rocks dip in all directions. And so this one is actually an intrusive dome, but concept's still there, where all the rocks dip away from the middle. So this one's really cool. This is Mauritania. You can see it from like Google Earth 1,000 miles out. Zoom right in, you'll see this big bullseye concentric circle. And when you get in there, if you were to go here, you would find a very few number of igneous rocks. That's about it. You wouldn't find a big pluton. In fact, initially, the lack of a pluton made people think this was an impact structure. But what it actually is this intrusive dome where you have what's called a laccolith. It's a really shallow pluton that comes in at very shallow depths and deforms all the rocks on top that's pushed everything up and created this concentric circle situation that is a structural dome. It's intrusive dome is probably the more accurate term, but nonetheless, the structure is still there that all the rocks dip away from the central part, giving you these concentric circles. And this is just a really beautiful version to see what a dome looks like. You'll see domes. The Black Hills are a dome. Doesn't necessarily show up as beautiful as this, which would be the opposite of a basin. So if you see a geologic map of the Black Hills, you'll see that concentric bullseye shape. Just like if you see the Michigan Basin, you'll see concentric circles, but all the rocks dip towards each other, which also means the youngest rocks are in the middle in the Michigan Basin. The Black Hills, the oldest rocks are in the middle. It's like anticlines on all sides for the dome, synclines on all sides for the basin.